The models are projecting a scenario with a chilling historical precedent. The last time our planet witnessed something similar was in 1877, an event that led to a famine claiming tens of millions of lives. And yet, here in early May, with summer still weeks away, we are seeing structurally unprecedented heat records being broken on both coasts of the United States at the same time. Phoenix is climbing toward 110 degrees, while Florida is seeing 155 years of weather history rewritten, with overnight temperatures refusing to dip below 80. All of this is unfolding before the main climate event has even officially commenced. This raises a profound question that will guide our journey. If these are merely the preliminary signals, what will the primary event itself bring? The story is only just beginning. As subsurface ocean heat continues to rise and forecast models generate figures never seen before. Here at Calm Space, we are dedicated to monitoring the growing divergence between official predictions and the atmosphere's real-time behavior. It is a story you will want to follow as it develops. We begin with the signal that precedes the main event, a phenomenon that seems as if it should not be possible, yet is unfolding before our eyes. At this very moment, two distinct heat domes are intensifying over opposite coastlines of the same nation, separated by thousands of miles, but reaching their peak intensity within the same 24 to 48-hour period. Perhaps more telling than the event itself is the reaction of the forecasters observing it. There is no alarmist shouting. Instead, a profound quiet has fallen. For anyone familiar with the scientific community, this quiet is often a far more ominous sign than any loud declaration of emergency. The first indication that something is amiss often lies within the data itself. In the desert southwest, for instance, the Salton Sea is projected to reach 112 degrees Fahrenheit. The city of Phoenix is experiencing a temperature trajectory that resembles a relentless upward climb. 104 degrees, then 108, and onward to 110. These figures are approximately 10 degrees higher than the climatological average for this time of year. It is a stark reminder that this is not late June or the height of August, but only early May. The desert is already exhibiting mid-July conditions before summer has even officially begun, a temporal displacement that is deeply concerning. What elevates this situation from unusual to extraordinary is what is happening on the other side of the continent. As the Southwest endures one high-pressure system, Florida is simultaneously being subjected to an entirely separate one. In Jacksonville, a city with 155 years of continuous weather data, long-standing records are now being surpassed, with Miami and Orlando close behind. The National Weather Service has issued its highest-level alert for South Florida: extreme heat risk. Such a classification is uncommon at any time of year, but for early May, it is almost without precedent. Amid the official bulletins and quiet discussions among meteorologists, one number surfaces repeatedly: 80 degrees Fahrenheit. This is the overnight low in some of South Florida's coastal regions. A drop from 100 degrees to only 80 does not represent recovery. It is merely a holding pattern. This lack of cooling means that the human body, the electrical grid, and the very infrastructure of the cities have no opportunity to shed the immense heat absorbed during the day. The cumulative stress this places on a population is a critical part of this story, one we will explore further. The scale of this event becomes clearer when we consider the human element. Approximately 450,000 people in California are under extreme heat watches, an official warning that the impending conditions pose a genuine physiological danger, moving beyond simple caution. But the impacts of this single, overarching atmospheric pattern are not limited to heat alone. While both coasts are experiencing these temperatures, the same system is also responsible for 8 active red flag warnings across the northern plains, creating conditions where one spark could ignite a disaster. Simultaneously, a corridor of severe weather risk is developing over Oklahoma and northern Texas. This is not merely a heat event, with 4 distinct extreme hazards unfolding across 2 coasts, all driven by one weather pattern. It is a comprehensive stress test for the entire system, taking place in just the first week of May. Yet, what truly elevates this beyond a remarkable week of weather is the global context in which it is occurring. All of these events are happening concurrently, during the very same week that major institutions began to sound a coordinated alarm. The Boston Globe featured a front-page story warning of a potentially record-breaking El Niño. Time magazine explored its global implications, while the Weather Channel started to frame the phenomenon as a super El Niño. At the same time, the World Meteorological Organization released a formal warning about its rapid development in the Pacific, and the National Oceanic and Atmospheric Administration, or NOAA, increased its own probability estimates. It is rare for so many institutional signals to align so perfectly. Their convergence suggests the underlying data is changing so quickly and clearly that it is compelling them all to act in unison. To summarize the situation, we are witnessing 2 heat domes on opposite coasts peaking within the same 4-8-hour window. Nearly 500,000 people in California are facing extreme heat alerts. A 155-year-old record in South Florida is under threat. And all of this is unfolding as the world's foremost climate organizations warn that the most powerful El Niño in recorded history may be in its infancy. The critical point is that these events are not coincidental. They are deeply interconnected. Understanding this connection is the central purpose of our exploration. To appreciate the gravity of this moment, it is important to understand what a heat dome is and what it is not. Heat domes themselves are not uncommon. Forecasters observe them forming annually in various regions. While some can be intense and even break records, they are typically localized phenomena, concentrating heat over one area before dissipating. What is occurring now, however, is structurally different in a way that requires careful consideration. We are observing what is known as dual node activation, 2 separate ridges of high pressure, separated by a continent, being sustained at the same time by a single, coherent atmospheric wave. This is not simply 2 heat domes, it is a categorically different event. And this leads to the quiet, unanswered question among meteorologists. They are not asking if this is bad, they already know it is. The question they are grappling with is whether this is an early signal from a climate system that is already behaving as if it has reached its peak phase. Some meteorological models are now displaying a weather system that, according to some analyses, has no precedent in the modern history of operational forecasting. If our climate is capable of generating these twin heat domes on opposite coastlines during the early pre-season of May, even before an El Niño has been officially declared, what might unfold when that pattern reaches its peak? This is not a rhetorical exercise. It is the very question that holds those who professionally monitor atmospheric systems in a state of what can only be called calibrated alarm. This isn't panic or drama, but a measured concern, the kind that makes experts cautious in their public statements, because they are not entirely certain their models are operating within the parameters they were designed to handle. We will explore every facet of this event, examining why the atmosphere is arranged in its current configuration and what the geometry of this particular pattern implies for its persistence. We will also investigate why the timing is perhaps the most significant anomaly of all, what is happening beneath the surface of the Pacific Ocean, what the forecast models are actually showing, and why some of them forced meteorologists to literally expand the scales on their charts just to accommodate the data. But before delving into the mechanics of the atmosphere, it is worth pausing on the signal itself, because that is where this story began. 2 coasts, 1 week, and the same powerful pattern emerging before the season has even started. Everything else we are about to explore is an attempt to explain why this anomaly is no coincidence, and why the people who dedicate their careers to these patterns are observing this week with an intensity usually reserved for disasters already in progress. The atmosphere has sent a signal. The question is whether we are interpreting it correctly. To comprehend why two immense heat domes are simultaneously cresting on opposite sides of the United States, one must first understand a specific structure in the upper atmosphere. This configuration, known as an omega block, may sound technical, but the concept is straightforward, and it is the architectural key to everything unfolding this week. We can visualize the upper atmosphere as a vast flowing river. This is not a narrow, contained channel, but a wide, meandering current, much like one that carves long, looping curves across a floodplain. This atmospheric river is the jet stream, and it dictates where weather systems develop, the path they follow, and how long they remain in one place. Under normal conditions, this river flows in relatively gentle, broad curves across a continent. Weather systems are born within its current, travel along with it, and eventually move on. No single pattern is able to dominate for an extended period because the river keeps flowing. However, there are times when this atmospheric river is forced into a shape that, when viewed from above, resembles the Greek letter omega. This pattern is characterized by a high-pressure ridge in the west, a deep low-pressure trough in the center, and another high-pressure ridge in the east. When this occurs, the flow can lock into that distinctive shape, and its eastward progression essentially grinds to a halt. As a result, weather systems that form beneath the ridges, in this case, heat domes, do not travel onward and dissipate as they normally would. Instead, they remain stationary and intensify. The longer they sit, the more heat is allowed to accumulate in the air below them. This is the dynamic currently at play, and it is precisely why meteorologists are so focused on the structure of the pattern, not just the temperatures it produces. The western ridge is the feature responsible for the intense heat building over the southwest. It is anchored above the desert, which is already one of the warmest landscapes on the planet at this time of year. Meanwhile, the eastern ridge is the engine driving the heat in Florida. This second ridge is centered over the Caribbean, actively pumping warmth and moisture northward into a peninsula that is already subtropical in nature. Situated between these two powerful ridges is the trough, the central dip in the atmospheric river. It is this trough that is generating widespread instability across the plains. The dangerous fire weather in the northern plains and the corridor of severe storms through Oklahoma are all products of this same atmospheric wave. The ridges are producing the heat, while the trough is producing the volatility. It is one single pattern with multiple, far-reaching consequences. This brings us to a critical detail that separates the current event from a more typical heat dome scenario. These two ridges are not independent systems. They are not two separate weather phenomena that just happen to be occurring simultaneously. Instead, they are connected nodes on the same vast structure known as a Rossby wave train. That distinction is everything, as it explains both the scale and the stability of the pattern we are witnessing. Rossby waves are planetary scale oscillations that ripple through the atmosphere. They are, in essence, the great meanders in the atmospheric river we described earlier, named for Carl Gustav Rossby, who first described them mathematically in the 1930s and 1940s. These waves are the dominant force governing weather patterns across entire continents. When a Rossby wave is in a low amplitude state, the jet stream tends to flow in a relatively straight and rapid path. Weather systems are carried along quickly, and no single pattern has a chance to linger for too long. But when a Rossby wave enters a high amplitude state, its meanders become dramatically exaggerated. The ridges push far to the north, and the troughs dip far to the south. This slows the entire pattern down, allowing individual weather systems to become effectively locked in place for days or even weeks at a time. What we are observing right now is a textbook example of a high-amplitude Rossby wave configuration. The wave is not merely amplified, it is sustaining two distinct ridge nodes at the same time, one over the west and one over the east, with the connecting trough acting as a bridge between them. This is sometimes referred to as a split ridge structure, as opposed to a single continental ridge. The structure is noteworthy because it means the extreme heat is not concentrated in a single location where it might, at least, be contained. Instead, the warmth is being distributed across the system into two separate yet fundamentally linked cores of extreme temperature. Beneath each of these powerful ridges, a process called subsidence is taking place. This is simply the large-scale sinking of air. When air descends under a high-pressure system, it becomes compressed. And as any student of basic physics knows, compressing air causes it to warm. This is a fundamental principle of our atmosphere. The dry adiabatic lapse rate quantifies this effect, telling us that descending air warms at a rate of approximately 5.5 degrees Fahrenheit for every 1,000 feet it sinks. If you imagine a parcel of air sinking from 30,000 feet all the way to the surface, you can begin to appreciate just how much warming occurs from this descent alone. This is the invisible engine of the heat dome, generating warmth before the sun's energy even enters the equation. But the process does not end there. The high-pressure ridge does more than just force air downward. It also clears the sky of clouds. These clear skies then allow the maximum amount of solar radiation to reach the surface. The sun beats down, heating the ground, and the ground, in turn, radiates that heat back into the air from below. This surface heating works in tandem with the compressional warming from subsidence, creating a powerful feedback loop that traps and intensifies the heat day after day. It is this combination of atmospheric mechanics and direct solar energy that transforms a simple high-pressure system into a formidable and resilient dome of extreme heat. The extreme temperatures are the product of two mechanisms working in concert, one of which involves sinking air that heats the layers below it through compression. This interaction is a fundamental and well-understood aspect of atmospheric physics, the very process that creates heat domes. The science itself is familiar, documented, and entirely predictable. What is deeply unfamiliar, however, is the outcome this normal physics is producing. It is generating abnormal results in two separate locations simultaneously, during a month when such intensity should not be seen in either place. While the physics remains constant, the configuration, the timing, the scale, and the dual-node structure are all highly unusual. This distinction brings us directly to the central question of our exploration. The climate system is already exhibiting behavior characteristic of a peak phase, even before the event that would normally explain such behavior has officially begun. An active research conversation in atmospheric science is currently examining whether these high-amplitude wave configurations are growing more frequent. Some studies propose that the jet stream is becoming more meridional, that is, wavier, with more pronounced ridges and troughs as a result of global warming. The underlying idea is that, as the Arctic warms more rapidly than the tropics, the temperature difference that powers the jet stream weakens. This reduced temperature gradient could lead to a slower, more meandering atmospheric river. This area of research, however, is genuinely contested. Some scientists find compelling evidence for this change in the observational record, while others maintain that the data is too variable to support any firm conclusions yet. It is vital to be clear that this is not a settled scientific question. But here, the distinction between a long-term research question and an immediate observation becomes critical. What is not contested is the observational fact of what is happening right now. In the first week of May, a high-amplitude wave configuration is sustaining two distinct ridge nodes at the same time. Whether this specific pattern is becoming statistically more common is a subject for future research. That it is happening at this very moment is a simple, observable reality. And this observation is telling us something that years of statistical analysis will be needed to definitively confirm. Before we proceed, One more aspect of this atmospheric geometry warrants attention, as it connects this moment to an event from only a few weeks ago. This is not the first time in 2026 that forecasters have observed the upper-level pattern and felt a sense of unease. Back in March, a strikingly similar high-amplitude ridge behavior triggered one of the most extreme heat events of this century. That event broke over 7,000 daily records and more than 2,000 monthly records, including a national March temperature record of 112 degrees Fahrenheit, placing it among the most anomalous events in modern meteorological history. That was just 6 weeks ago. Now, we are once again witnessing a similar wave structure produce a comparable pattern of extreme ridge amplification. This time, however, it is occurring across 2 nodes instead of 1, and in a month that is typically much quieter. We have 2 major events, separated by only 6 weeks, both driven by high-amplitude ridge behavior and both far exceeding what seasonal norms would predict. The geometry of the atmosphere seems to be showing us something profound. That the system is already functioning in a mode that feels far more energetically advanced than what early May should look like. The reason this matters, and the reason it connects to the warnings from climate institutions about El Niño that same week, is that the atmosphere is not supposed to be reacting this way yet. If the system is already responding with such intensity, it suggests that something in the underlying ocean conditions is already pushing it. To understand what that something might be, and to see what the Pacific Ocean is doing beneath the surface right now, is where our journey takes us next. To fully grasp the significance of these events, we must first understand a concept in weather forecasting that is fundamental, even if it rarely enters public discussion: the climatological normal. While it may sound bureaucratic, this idea is essential. A climatological normal is, in essence, what the atmosphere is supposed to be doing on any given day of the year. It represents the average temperature, pressure, and frequency of weather patterns, all calculated from a 30-year baseline. This normal is the expectation, the benchmark against which any single weather event is measured. Forecasters identify anomalies by calculating how far a specific observation deviates from this established expectation. For Phoenix, Arizona, in early May, the climatological normal for daily high temperatures is in the low to mid 90s Fahrenheit. A temperature of 110 degrees Fahrenheit is not a minor deviation. It represents a departure of roughly 15 to 17 degrees, depending on the exact date. In statistical terms, this is an event that falls several standard deviations outside the expected range. In practical terms, it means that, in the first week of May, Phoenix is enduring heat that would be considered extreme even at the peak of summer in mid-July. This is the timing anomaly. One could argue that this timing anomaly is, in some ways, more significant than the temperatures themselves. The reason lies in the seasonal evolution of the atmosphere. In the southwest, the persistent high-pressure system, or seasonal ridge, that brings the extreme heat of June, July, and August is not yet fully established in early May. The atmospheric pattern that produces 110-degree days in Phoenix in late June exists because the entire regional system has spent months preparing for it. The soil is already hot, regional moisture has been depleted, and the atmospheric boundary layer has been conditioned to amplify heat. By late June, all these preconditions are met. In early May, they are not. And yet, the temperatures are arriving as if they were. This heat is materializing without the seasonal infrastructure that normally supports it. It is like a building collapsing not from a weak foundation, but because it was subjected to its maximum load before the foundation was ever poured. The stress is arriving before the system has had a chance to prepare for it. Florida's situation tells the same story, just from a different angle. The state's weather history is defined by a pattern where extreme heat truly intensifies in June and July. This is when a combination of high sea surface temperatures, moisture-rich air, and persistent high pressure creates the oppressive conditions familiar to residents. The records, now being challenged at stations, with 155 continuous years of data, were set during those peak summer months, and they are being challenged in early May. This raises an important question, one that must be asked honestly. When we observe an extreme weather event, a crucial question emerges. Is it merely an isolated occurrence, or does it signify a more profound systemic change? Answering this requires careful and precise language. Any single heat event, regardless of its intensity, cannot on its own prove the existence of a larger trend. Weather is, by its very nature, variable. Outliers are a statistical certainty, and anomalous events have always been a part of Earth's climate history. Therefore, a scientist who claims that one heatwave is definitive proof of climate change is overreaching. But the narrative begins to shift when we move our focus from a single event to an emerging pattern. The situation becomes more complex because we are not examining one anomalous event, but two occurring just 6 weeks apart. Both of these events surpass the predictions of the established climatological baseline, and both took place outside their typical seasonal window. They were also driven by similar atmospheric patterns, specifically high-amplitude ridge configurations. This is all happening against a backdrop of multi-year data, which reveals that extreme heat early in the season has been occurring with growing frequency. A single outlier is just that, an outlier. But two such events, separated by only weeks in the same season, following a year of unusual ocean warmth, and coinciding with major climate institutions raising their El Niño probability forecasts, suggests a pattern that demands our serious attention. The discomfort among forecasters is not rooted in the heat itself, as they have experience with extreme temperatures. Instead, their unease stems from the calendar. The climate system appears to be behaving as if it were months ahead of schedule. This challenges the very conceptual frameworks that forecasters rely upon, where seasonal boundaries help them distinguish what is normal for May versus what is normal for August. When these foundational baselines become less reliable, the ability to contextualize current events is compromised. More critically, this erosion of certainty degrades the capacity to issue effective public warnings. This is not simply a matter of scientific curiosity. It is an operational problem with tangible consequences. Consider the implications of the extreme heat risk classification being triggered in South Florida during early May. This classification represents the highest level of a tiered alert system, which is designed to convey the risk of serious physiological danger to the public. Its thresholds are carefully calibrated against historical data on heat-related illness and mortality. When such an alert is issued in July, it is already a cause for alarm. But when it is triggered in early May before the public, healthcare systems, and infrastructure managers have fully transitioned into their summer heat preparedness mindset, it reveals a hidden vulnerability. The danger in this case is amplified not just by the intensity of the heat, but by its unseasonable timing. Beyond this, something more subtle is occurring that links this timing anomaly directly back to the central question of where our climate system is headed. The quiet apprehension among forecasters is not just that the heat has arrived early, but that it has arrived early into an environment where the ocean is already preconditioned. When we witness early season atmospheric extremes coinciding with the highest ever recorded subsurface Pacific Ocean heat for the month of April, we are likely not observing two unrelated phenomena. This may be a sign that the oceanic preconditioning is already influencing the atmosphere in ways that shouldn't be observable yet, because the formal El Niño event that these ocean conditions portend has not even officially begun. This is the detail that raises a flag, not the temperature records themselves, but the timing. The atmosphere is responding to something, and that something is happening ahead of schedule. The question of how a system behaving this way so early in the year will act when the seasonal peak finally arrives is not academic. It is the fundamental question. Before exploring the Pacific's behavior and the projections from climate models, another dimension of the current event warrants its own focus. It is this dimension that can transform an extreme weather event into a genuine humanitarian crisis. The nights are no longer cooling down. This lack of overnight relief presents a problem that extends far beyond simple discomfort. The human body is an incredibly sophisticated thermal management system, employing mechanisms like sweating, dilating blood vessels to release heat, and breathing faster to cool itself. Under most conditions, it is extraordinarily effective at maintaining its core temperature within the narrow 97 to 99 degree Fahrenheit range, essential for its biochemistry. However, this entire system relies on one critical factor that is often overlooked in discussions of heat waves. It needs time to recover. During the day, the body accumulates what physiologists refer to as a heat load, which is the net thermal stress imposed by the environment. Even if the body successfully manages this stress during daytime hours, preventing a dangerous rise in core temperature, it does so at a significant physiological cost. Electrolytes are depleted, the cardiovascular system is strained, and blood flow is redirected from vital organs to the skin. The body is working incredibly hard, and like any system under strain, it requires a period of recovery. For the human body, that recovery window is the night. When overnight temperatures fall into the 60s or lower, the body is granted this crucial recovery period. The thermal load from the environment diminishes, sweat evaporates efficiently, and the core temperature can drop naturally. The cardiovascular system returns to its baseline state. By morning, the body is reasonably prepared to face another day of heat. But when overnight temperatures remain in the upper 70s to low 80s, as they have been in South Florida, that recovery window vanishes. The body is never able to fully offload the thermal stress from the previous day. Each new day of heat layers on top of the residual load from the day before. It is this accumulation that proves so dangerous, not a single moment of extreme heat, but the compounding effect of stress that never fully resolves. Consequently, day 2 of a heatwave with warm nights is far more dangerous than day 2 of a heatwave with cool nights, even if the daytime temperatures are identical. The language used by the National Weather Service to describe the current conditions is precise and telling. Stagnant, soupy, uncomfortable. These are not dramatic words. They are accurate descriptors of a dangerous situation. The atmospheric ridge overhead suppresses wind, preventing the air near the surface from being mixed or refreshed. Combined with high humidity from the Caribbean, the already saturated air makes it nearly impossible for sweat to evaporate, trapping heat against the skin. A convergence of conditions is unfolding: high humidity, still air, and overnight temperatures that refuse to fall. A ridge of high pressure has settled in, showing no indication of moving for days. This combination signals something far more serious than simple discomfort. It is the forecast for a genuine physiological crisis, one that poses a particular threat to the elderly, to those without air conditioning, and to outdoor workers who cannot retreat to a climate-controlled space. To place this event in context, consider a typical night in early May in Miami. Temperatures usually descend into the upper 60s or low 70s, creating a significant 17 to 20 degree difference between the day's high and the night's low. This is a gap you can feel when you step outside after sunset, a sense of release as the air changes. But right now, that gap has shrunk dramatically to between 20 and 25 degrees on a good night, and in some coastal areas, as little as 12 to 15 degrees. Overnight lows, remaining above 80 degrees in South Florida during early May, are not part of the normal climatological pattern. In fact, they are more aligned with the intense conditions of peak summer, raising the question of how our bodies and our cities can cope with such an unseasonable strain. This phenomenon has implications that extend beyond individual health because our cities themselves function as massive thermal systems. The buildings, roads, and the vast expanses of concrete and asphalt that constitute the urban fabric all absorb solar heat during the day. At night, they are meant to release it. This is the well-known urban heat island effect. However, this process is being amplified by the very same conditions that prevent our bodies from cooling. Stagnant air and high humidity, with no wind to carry heat away from these surfaces. When the nights stay warm, the city never fully sheds the heat it absorbed. With each passing day, it begins from a slightly higher thermal baseline, accumulating heat with no chance for release. This sustained heat places an immense burden on the city's infrastructure. It is not the single peak temperature of a hot afternoon that pushes the power grid to its limits. Rather, it is the unrelenting, continuous demand from millions of air conditioners that never cycle off because the nights never become cool enough for people to simply open their windows. The water systems, struggling to maintain pressure, also experience this constant load without any period of recovery. This is the process by which a heat wave transforms from an acute, single-day event into a multi-day crisis. The system is denied the rhythm of rest and recovery it was built to expect. The true danger of a heat wave lies in its persistence, not just its peak intensity. The greatest number of heat-related emergency room visits does not occur on the hottest afternoon. Instead, it happens on the third or fourth day of elevated overnight temperatures, when the body's accumulated physiological debt becomes too great to manage. Our bodies, like our cities, depend on the cool of night to recover. When that relief is denied, the stress compounds. The relentless nature of the heat is what makes this event so hazardous, ensuring it persists rather than releases its grip. A single, powerful insight captures the entire situation. Cities do not fail because of the heat itself. They fail in their ability to recover from it. The heat is the stressor, but the nights without cooling are the mechanism of failure. What makes this particular moment so significant is its timing. This failure mode is appearing in early May, long before public health agencies, utility companies, hospitals, and emergency management have fully activated their summer heat protocols. The season has not officially shifted, and the system has not been formally warned, yet the crisis-level conditions have already arrived. All of these elements, the dual ridges of high pressure, the unseasonable timing, the high overnight temperatures, and the compounding hazards, are ultimately symptoms. To truly understand why these symptoms are manifesting now, and what they might foretell for the future, we must look deeper than the atmosphere. Our investigation must take us into the vast expanse of the ocean. The story beneath this story is unfolding in the Pacific, and its implications may be even more profound than anything happening in the skies above. Before we journey into the Pacific, however, it is essential to have a clear understanding of the physics at play overhead. There is a tendency in weather reporting to focus on temperature records and danger levels, often without explaining the actual mechanism driving the heat. But the mechanism is critical, as it directly connects to the intensity of this event. The high-pressure systems anchored over the Southwest and the Caribbean are not creating heat from nothing. They are transforming energy already present in the atmosphere into thermal energy through a process known as adiabatic compression. Within a high-pressure system, air is continuously forced downward in a process called subsidence. As this column of air sinks toward the surface, it is compressed into a smaller volume by the increasing atmospheric pressure below. This very act of compression generates heat. The physics are the same as what makes a bicycle pump feel warm as you use it. Energy is not being created, but rather converted from the kinetic energy of compression into thermal energy. The dry adiabatic lapse rate, a warming of 5.5 degrees Fahrenheit for every 1,000 feet of descent, is the scientific principle that quantifies this effect. To illustrate the power of this process, consider a parcel of air sinking from an altitude of 30,000 feet. Through compression alone, its temperature would increase by approximately 165 degrees Fahrenheit before any other factors are even considered. Of course, the air at that altitude is initially very cold, so the net effect on the ground is not that extreme in practice. Nevertheless, the contribution of compression to surface temperatures under a heat dome is substantial. It is a powerful reminder that the heat we feel is not just from solar radiation, but from solar radiation working in concert with the immense weight of the atmosphere itself. The high-pressure ridge introduces another critical factor: clear skies. By suppressing cloud formation, the ridge allows the sun's energy to reach the surface without interruption. This direct solar radiation heats the ground in the case of the southwest, desert ground with a very low albedo, which absorbs nearly all the energy that strikes it. This heated ground then radiates long-wave energy back up into the atmosphere. The result is a powerful feedback loop. The sinking air, already being warmed by compression from above, is now also being heated from below by the radiating ground. Both mechanisms operate simultaneously, amplifying each other. This is all well understood physics. There is nothing mysterious about the process itself. For decades, forecasters have modeled how a heat dome forms and produces these conditions, leading to extreme temperatures. The true scientific frontier, the question that now confronts us, is why this normal, predictable set of physical laws is producing outcomes on this scale, at this time, and in this particular configuration. We are witnessing normal physics yield abnormal results. And it is in the gap between what the mechanism should predict and what our observations reveal that the central, urgent question of our time resides. The physics tells us how this is happening, but it does not yet tell us why it is happening like this, now. The timing and scale of this event suggest that something far upstream, within the vast mechanics of our global climate system, is preparing the way for a much larger phenomenon than the season would normally allow. This is precisely why forecasters are approaching the situation with a quiet intensity rather than routine analysis. While they grasp the physics of what they are observing, the underlying reason for the system expressing itself with such force, so early, remains a profound question. Let us reframe what is unfolding this week, because describing it merely as a heat wave is accurate, yet fundamentally incomplete. What is truly taking place is a compound hazard event. Understanding it in this way, as a cascade of interconnected dangers rather than a singular heat wave, completely alters our perception of its significance and its risk. If we return to the atmospheric configuration we previously discussed, the Omega block, with its western and eastern ridges and the trough between them, we can see how this unfolds. Each element of that pattern is not generating just one type of extreme weather. It is producing multiple, simultaneous extremes that overlap in both time and space. Each of these extremes then interacts with the others, creating a systemic stress that cannot be captured by assessing any single hazard in isolation. The Western Ridge, for instance, is responsible for the oppressive heat dome settling over the southwest. This has driven temperatures to 112 degrees Fahrenheit at the Salton Sea and put Phoenix on a trajectory toward 110 degrees, placing 450,000 Californians under extreme heat watches. This is the first hazard, but the same atmospheric process is also creating the perfect conditions for fire weather throughout the region. The very subsidence that causes extreme heat also strips moisture from the atmosphere, pushing relative humidity down to levels where any spark can become immediately dangerous. For this particular event, however, the most acute fire weather is not in the southwest. It is located in the northern plains, where the dynamic interplay between the ridges and the trough is generating the exact conditions that forecasters dread when it comes to wildfires. Powerful winds, exceptionally low relative humidity, and critically dry vegetation. The 8 active red flag warnings across the northern plains are not a separate phenomenon. They are a direct consequence of the same atmospheric wave pattern produced through the mechanism of the trough. This constitutes the second major hazard. At the same time, the trough situated between the ridges is creating yet another threat. Where its cold air meets the warm, moist air being drawn northward from the Gulf of Mexico, a flow amplified by the eastern ridge, the ingredients for severe thunderstorms come together. This combination produces atmospheric instability, abundant moisture, and significant wind shear from the clash of the two pressure systems. The result is a corridor of severe weather risk across Oklahoma and northern Texas, marking the third hazard. Meanwhile, across the Gulf and extending up through the Florida Peninsula, the eastern ridge is producing its own set of dangers. This includes sustained, oppressive heat, elevated overnight temperatures that offer no relief, and high humidity, all of which cause immense physiological stress and strain on the power grid. In Jacksonville, these conditions are challenging records that have stood for 155 years. This is the fourth simultaneous hazard, all stemming from a single atmospheric setup. The operational challenge this creates is worth pausing on, as it is not merely a logistical problem, but a potential resource allocation crisis. Emergency management agencies operate with finite capacity. When they are tasked with simultaneously managing a heat emergency affecting 450,000 people in California, a fire weather emergency across 8 distinct regions of the northern plains, a severe storm corridor in the southern plains, and a heat health crisis across the entire Florida peninsula, something has to give. With the same personnel, the same communication infrastructure, and the same budget for public attention, some areas will inevitably receive less focus than they require. The compound nature of the event is itself a risk factor, independent of any individual threat. This is not the first time in recent years that a single synoptic pattern has generated such a multi-hazard cascade. This phenomenon is part of what has led some researchers to focus on the question of atmospheric energy. The argument, which I want to clearly flag as an active research question rather than a settled conclusion, is that a more energetically charged atmosphere may amplify the extremes that each component of a given pattern can produce. With more energy in the system, the peaks of the ridges become higher, the troughs become deeper, more moisture is transported, and more wind shear is generated across boundaries. To put it another way, imagine a fire that has been burning steadily for hours. If you throw more fuel onto it, the same physics of convection that were producing a moderate flame will now produce a much larger one. The fundamental physics did not change. The energy input did. The question some atmospheric scientists are beginning to carefully ask, with all appropriate uncertainty, is whether our climate system is behaving like a fire that has been given more fuel. Are we seeing the same wave patterns and pressure configurations, governed by the same physics, but with more extreme outputs because the underlying energy budget of the system has shifted? This is, admittedly, a speculative framing, but it is a perspective that the current event makes difficult to dismiss, precisely because it is occurring before the El Niño that would supply such an energy increase has even formally begun. If this is what the prelude looks like, with the system already producing 4 simultaneous extreme hazards across the continental United States in the first week of May, then the question of what happens when the peak actually arrives is not rhetorical. It is operational. Emergency managers and utility companies need to be asking it, and they likely are, quietly, in the same way that forecasters are watching their model outputs without being ready to say publicly what those outputs are showing them. The event that unfolded in March was not an isolated occurrence. Before we turn our attention to the Pacific to see what the ocean is doing, we must pause on something that received significant coverage in March of 2026, and then, like most weather events, largely faded from public attention once it was over. As it turns out, March was not a standalone incident. When you examine both events together, the one in March and the one happening now, a pattern begins to emerge that changes how one must interpret what we are currently watching. In March of 2026, an immense heat dome settled over the United States, unleashing an event that left even seasoned meteorologists searching for words. Its scale was breathtaking, obliterating more than 7,000 daily temperature records and over 2,000 monthly benchmarks. The national temperature for March soared to an astonishing 112 degrees Fahrenheit, a figure so high that experts noted it seemed to belong to a completely different season. When measured against its departure from normal climate expectations, this event was ranked among the most severe heat waves recorded in the entire century of modern weather observation. It was a phenomenon that seemed to defy the established patterns of the past. The atmospheric engine driving this March anomaly had unique characteristics. Its origins were linked to a Kona storm, a specific kind of upper-level low-pressure system that develops near Hawaii. These storms are known to influence the North American jet stream in ways that remain difficult to forecast over longer periods. In this case, the Kona storm's influence was crucial, contributing to the amplification of a high-pressure ridge that generated the extreme heat. This complex interaction offered a partial explanation for why the event was so challenging to predict well in advance. At the time, the particular convergence of these factors appeared to be a rare, almost singular alignment, an extraordinary but seemingly isolated occurrence. But the event was not isolated. Just 6 weeks later, during the first week of May, a high-amplitude ridge with a strikingly similar structure began to form, producing the phenomenon we are witnessing now. This time, however, the configuration is different. It features 2 distinct nodes instead of one. As a result, it is unfolding on both the east and west coasts at the same time, triggering a complex, multi-hazard situation rather than a focused regional one. While the March event was defined by its sheer intensity, this current one is characterized by its breadth. Placing these 2 powerful events side by side raises an immediate and unsettling question about what is unfolding in our atmosphere. What, then, are the statistical odds of 2 such powerful events taking place within a mere 6 weeks of each other, in the very same season? Within a climate system that is behaving according to its historical patterns, the probability is exceptionally low. These are the types of occurrences that, in the past, had return periods measured not in weeks, but in decades or even longer. To witness 2 of them, born from similar atmospheric setups in such a short span, represents a statistical anomaly. Such a profound departure from the norm is significant enough to suggest that the climate system itself may no longer be operating within its familiar range of variability. This is not a political assertion, but a conclusion drawn from the language of probability. It is important to be clear about what this observation implies, and what it does not. This does not mean that any single weather event can be definitively assigned to a specific cause. The science of attribution is a careful and sophisticated field that avoids making simple declarations about individual occurrences. What it does mean, however, is that the appearance of 2 events on the scale of a 500-year disaster within 6 weeks of each other is a signal. It is a signal that warrants serious and immediate attention from both researchers and policymakers. What makes this sequence particularly compelling and relevant to our central question is the backdrop against which both events have occurred. The March heatwave and the current one are both unfolding against the canvas of a Pacific Ocean that is warming with unusual speed. Subsurface heat has reached levels never before recorded for this time of year in the satellite era. This is all happening at the very moment the world's climate institutions are elevating their probability estimates for what could become the most powerful El Niño ever documented. The March event can be seen as the first signal. The current event, arriving so soon after, is the second, and both of these signals have appeared before the very phenomenon that might explain them, the El Niño, has even been formally declared. This particular sequencing is what sounds the alarm. It suggests the climate system is already expressing something in the atmosphere, consistent with a system much further along in its transition than our official monitoring tools indicate. If the atmosphere is already responding to the Pacific's developing state before that state crosses our formal thresholds, it implies a critical mismatch. Our monitoring frameworks may be telling us what phase we are in, while the atmosphere is already behaving as if it's in a different phase entirely. This discrepancy is precisely what has forecasters quietly unsettled, and it is what now turns our attention to the Pacific. Part 8. The Pacific is already moving. There is a particular region in the tropical Pacific Ocean, an area roughly centered between 170 degrees west and 120 degrees west longitude, that straddles the equator. This area is known as the Niño 3.4 region. On a map, it appears as a simple rectangular patch of deep blue water, seemingly unremarkable, adrift in the middle of the world's largest ocean. But this specific patch of water is, for all practical purposes, one of the most important pieces of geography on our planet. The reason for its significance is that the temperature of the water in this very region drives atmospheric circulation patterns on a global scale. It dictates rainfall, drought, temperature, and storm activity across nearly every inhabited part of the world. When the water here is warmer than average, the atmosphere responds with a cascade of global weather shifts that we call El Niño. When the water is cooler than average, the opposite pattern, known as La Niña, takes hold. For the past several years, the Pacific has been locked in a La Niña-dominated state. This has meant cooler than average waters in the Niño 3.4 region, with a corresponding global pattern, increased rainfall in the Western Pacific and Australia, and suppressed rainfall in the Eastern Pacific and the Americas, along with altered storm tracks over North America. La Niña has served as the baseline condition for so long that it has become a normalized part of the framework for both public and operational forecasting in the United States. But that baseline is now changing, and the speed of that change is what is causing the modeling community to produce outputs that are at once their most sophisticated and their most uncertain. Approximately 6 months ago, the surface temperature of the Niño 3.4 region started to warm. As of the latest data, that warming has reached about 0.66 degrees Celsius above the long-term average. On its own, that number would be noteworthy, as it marks a clear departure from the La Niña baseline and places the region in what is called ENSO-neutral territory, trending toward an El Niño. But the surface temperature is not the most significant figure in the current dataset. The most telling number, the one that holds the key to what may come next, lies beneath the surface. In the upper layers of the ocean, from the surface down to 300 meters, a staggering amount of thermal energy is being stored. As of this April, the subsurface ocean heat content has reached the highest level ever documented in the satellite observational record. This era of monitoring, spanning roughly 4 to 5 decades, provides a continuous stream of data, and within that entire history, the ocean has never held this much warmth in April. This hidden energy surpasses what was seen during the build-ups to the landmark El Niño events of 1997 to 1998 and 2015 to 2016, which were the strongest of their time. The current situation is, in this specific measure, without precedent, prompting us to ask what this accumulation of deep warmth truly signifies. To appreciate the gravity of this, it is essential to distinguish between the heat hidden below and the temperature at the very surface. A simple analogy can help clarify this critical difference. Consider a pot of water being heated on a stove from the bottom. The subsurface heat content is like the energy that has already permeated the lower depths of the water but has not yet reached the top. An observer watching only the surface might not see the full picture of how much energy the system contains. The real story is unfolding below, a silent buildup of power. In oceanographic terms, this immense reservoir of subsurface heat in the Pacific is a clear precursor to future surface warming. It is the quiet before the storm. This deep pool of warm water is not destined to remain hidden. A combination of oceanic and atmospheric processes, including upwelling, mixing, and shifts in trade winds, will inevitably bring that energy to the surface. As this heat emerges, it is expected to drive the surface temperatures in the crucial Niño 3.4 region of the Pacific sharply upward, in ways that current surface readings do not yet reveal. Scientific models are able to perceive this impending change. They can see the subsurface heat reservoir and calculate, within a certain range of uncertainty, how this stored energy will translate into surface conditions in the months ahead. The projections they are generating are so extreme that some forecasting systems have literally had to expand their graphical scales to accommodate the data. Before delving into those startling numbers, it is vital to connect this oceanic picture back to the atmosphere. One of the most compelling and debated areas of climate science involves understanding when and how the atmosphere begins to react to changing ocean conditions. In a typical El Niño development, the process is sequential. The ocean warms past a certain threshold. This tropical heating drives atmospheric convection, which in turn alters global circulation patterns like the Walker circulation and the jet stream, ultimately changing weather across the planet. It's a time-lagged chain of events, first the ocean, then the atmosphere. This is the standard model. However, a scientifically serious and cautious line of inquiry is now exploring a different possibility. Some researchers are examining whether the unusual atmospheric behavior we see now, the high-amplitude wave patterns and early-season heat extremes, might already be a response to the ocean's time's subsurface condition. This would mean the atmosphere is reacting before that deep heat has fully manifested at the surface. If this is the case, the standard model of El Niño development may underestimate how quickly and forcefully the atmosphere can respond. It would suggest that by the time the surface temperatures catch up, the atmospheric patterns are already primed and configured, ready to amplify the ocean's signal. This interpretation, while speculative, is a scientifically rigorous one. It is precisely this kind of possibility that makes the timing and nature of the current heat events so deeply significant. The atmosphere may be responding to a signal that standard surface measurements are not yet fully capturing. If this hypothesis proves correct, then the anomalies we are witnessing today are not just isolated events. They are a preview of a much larger shift on the horizon. There are moments in science when the data is not just significant, but genuinely paradigm-shifting. These are times when the best models produce numbers they have never produced before, forcing researchers to redraw the very graphs that have been used for decades just to fit the new reality. This is the extraordinary situation that some of the world's leading El Niño forecasting teams are now facing. To provide context for these new figures, we must look to the past. The two most powerful El Niño events in the modern record occurred in 1997 to 1998 and 2015 to 2016. At their peaks, these events caused the sea surface temperature in the Niño 3.4 index region to rise by approximately 2.4 and 2.6 degrees Celsius, respectively, above the long-term average. These were extraordinary deviations that triggered global weather disruptions still used as benchmarks for disaster planning, including devastating floods, droughts, altered storm tracks, and agricultural failures. Now, consider this. The multi-model ensemble median for the developing El Niño is currently projecting a peak anomaly of approximately 2.9 degrees Celsius. Let that number settle for a moment. At 0.3 degrees above the 2015 to 2016 event, and half a degree above the 1997 to 1998 event. These are not marginal increases. In the language of Earth systems, these are substantial leaps into a more extreme state. The relationship between the magnitude of an El Niño and its global weather impacts is not linear. It is closer to exponential. A 2.9-degree event is not merely a little stronger than a 2.6-degree event. Its capacity to disrupt precipitation, drive drought and flood, and alter temperature baselines across vast portions of the planet is considerably greater. A small increase in the peak number can lead to a disproportionately large increase in real-world consequences. And 2.9 degrees Celsius is only the median, the midpoint of the range of possibilities. Some individual models within the ensemble are producing outputs that extend beyond 3 degrees, with some projecting peak anomalies in the range of 3.5 degrees Celsius or even higher. The upper end of the probability distribution for this event extends into territory that has never been observed in the historical record. For a 3.5-degree anomaly in the Niño 3.4 region, there is simply no historical benchmark. We would be navigating entirely uncharted waters. When forecasting the weather, we rely on history. But what happens when there is no historical event to point to, no precedent that shows what our world might look like? This is the uncomfortable position climate scientists and meteorologists now find themselves in, forecasting the consequences of an event with no modern parallel. The situation became so extreme that the very tools used for forecasting had to be changed. The y-axis on the standard ENSO forecast graphics, which display model outputs for the Niño 3.4 anomaly, was never designed to show values exceeding 3 degrees Celsius. The operational systems generating these charts required modifications simply to accommodate what the models were predicting. When you have to update your visualization tools to fit the data, it's a clear sign you have entered unprecedented territory. This isn't alarmism. It is a simple description of what occurred in operational forecasting centers. There are, of course, important caveats to these figures, and we will explore the genuine scientific debate over their interpretation. But before delving into that discussion, the sheer scale of what these models are projecting must be understood. The median forecast for this El Niño suggests an event stronger than any ever recorded in modern history. The upper range of the predictions extends into a domain for which we have no observational benchmarks at all. All of this is being projected for a peak in late 2026, a moment still months away. Yet, the system is already powerful enough to drive dual-coast heat domes in early May, long before that peak is expected to arrive. This dissonance between the current, already extreme weather and a future, even more powerful peak raises profound questions about the months ahead. The institutional response to these staggering numbers has been swift and significant. The World Meteorological Organization issued a warning about the event's rapid development, which we noted earlier. In parallel, NOAA's Climate Prediction Center increased its probability estimates for El Niño. Major media outlets like the Boston Globe, Time, and the Weather Channel all featured the story in the same week that the atmospheric effects of the developing event were shattering 155-year-old records in Florida. This convergence of signals from institutions, media, and direct observation is no coincidence. It reflects the reality that the same data driving the institutional alerts is also producing the atmospheric conditions we can see in real time. In essence, the models are telling a story, and the atmosphere is showing us the first chapter. The urgent question that remains is what the later chapters will look like, and whether our framework for forecasting them is adequate for the magnitude of what is being suggested. Whenever scientific data ventures into genuinely uncharted territory, the scientific community does what it is supposed to do. It debates. The current El Niño forecast has ignited a substantive and serious debate among researchers and operational forecasters. The discussion is not about whether warming is happening or the general direction of the trend. Instead, it centers on a critical question: just how far beyond the historical record will this event actually go? And, flowing from that, Should the current model outputs be treated as reliable guides for action, or are they uncertain extrapolations beyond their validated ranges? This debate forces us to consider how we act in the face of profound uncertainty. To understand the situation, it helps to look at the two main perspectives, as this debate has real-world implications for how policymakers, emergency managers, and the public should prepare for the coming months. The first group, the high-confidence camp, points to the immense heat content stored beneath the surface of the ocean, which is at a record high for any April in the satellite era. They also note the rapid rate of warming over the last 6 months. For them, this evidence suggests that the trajectory toward an extremely powerful El Niño is already locked in. The reservoir of heat in the Pacific is so vast, and the physical mechanisms that will bring it to the surface are so well understood that they see the outcome as highly probable. Regardless of how atmospheric conditions evolve, this camp often uses definitive language, citing the unprecedented subsurface heat as primary evidence, and viewing recent heat events and model outputs as part of a single, coherent picture of a system already in an advanced state of transition. On the other side is the cautious camp. These scientists are not disputing the physics or the observations. Instead, they are raising methodological concerns about what happens when models are asked to forecast conditions outside their validated range. Every numerical model is calibrated against historical data. When a forecast phenomenon exceeds that historical range, the model must extrapolate rather than interpolate. This process of extrapolation introduces a fundamentally different kind of uncertainty. The cautious camp argues that projecting El Niño anomalies of 3 degrees or higher involves significant extrapolation uncertainty. To present those projections with the same confidence as those within the historical range is, in their view, epistemically overconfident. They label the most extreme forecasts as premature, not necessarily wrong, but not yet established with enough rigor to warrant high confidence. Both of these positions are scientifically legitimate. The disagreement is not ideological, but is centered on the difficult problem of handling uncertainty at the very edge of a model's performance. This is a healthy debate, reflecting the genuine challenge of forecasting at extremes. But this is precisely where the debate becomes directly relevant to the heat events happening right now. The dual coast heat domes are occurring in the gap between these two scientific positions. Their intensity is consistent with what the high-confidence camp would predict for a system already in advanced El Niño development. At the same time, they are more extreme than what the cautious camp would expect from a system that has not yet even formally crossed the El Niño threshold. The atmosphere, in early May, is already producing weather that seems to challenge the premature argument. The heat is not waiting for the scientific debate to be resolved. The records are being broken whether or not forecasters have settled on the ultimate magnitude of what is causing them, and perhaps this provides the clearest lens through which to view these events. The debate between definitive and premature is about what the numbers will look like at the peak, but the atmosphere is already providing powerful, observational evidence that contributes to that very debate. Every heat record shattered in Jacksonville, every night in Miami that remains above 80 degrees, and every afternoon in Phoenix that soars toward 110, all of these are data points. This accumulating data is currently trending in a direction that some observers see as a validation of their predictions. At the same time, a more cautious group notes that individual events, no matter how extreme, are insufficient to settle broad questions of long-term forecasting. Both perspectives are valid for the reasons they are held, and both are watching the unfolding situation with intense scrutiny. When forecasters and climate scientists attempt to envision the global impacts of a potentially record-breaking El Niño, they encounter a significant obstacle. There is no modern precedent to study. The entire historical record, from the satellite era back through the instrumental records of the late 19th century, simply does not contain an event of the magnitude that some models are now suggesting is possible. This forces researchers to look even further into the past, into the paleoclimate record itself. In that deeper history, only one event begins to approach the scale of what current models are projecting: the El Niño that occurred from 1876 to 1878. Climatologists have meticulously reconstructed this event using evidence from tree rings, coral archives, and historical documents. Their findings suggest a magnitude that may have surpassed anything witnessed in the subsequent century and a half. Its effects were global and utterly catastrophic. The drought it unleashed across South Asia contributed to a famine that resulted in the deaths of tens of millions. China endured its own devastating drought and agricultural collapse, while East Africa, Brazil, and Australia were all severely impacted by the disruption to worldwide rainfall and temperature patterns. In historical terms, it's still one of the most consequential climatic events ever recorded. It is critical, however, to be very careful in how this historical analogue is presented, as it is easy to arrive at the wrong conclusions. The 1876 to 1878 El Niño is not a direct prediction of what a future event might bring. The climate system of the 1870s was fundamentally different from that of the 2020s in several crucial ways. Global average temperatures were roughly 1.5 degrees Celsius cooler than they are today. The background atmospheric CO2 concentration was at a pre-industrial level. The distribution of warm and cool ocean waters was different, and the world's population and agricultural systems were structured in a completely different manner. So, what purpose does this analogue serve? It provides a vital sense of atmospheric and oceanic magnitude. It is a data point that illustrates what a tremendously powerful El Niño looks like in terms of its intensity and duration, as measured by metrics like the Niño 3.4 anomaly. It does not, however, tell us where the impacts will fall in the modern world or with what severity, because the baseline climate onto which this signal would be superimposed is now so profoundly different. This brings us to the most useful and urgent question the analogue raises. What happens when you layer an El Niño signal of historical magnitude onto a baseline climate that is already warmer than it has been in thousands of years? The El Niño phenomenon itself adds anomalous warming on top of the existing background temperature. Given that this background temperature is now more than 1 degree Celsius higher globally than it was in 1877, an equivalent El Niño signal would inevitably produce higher absolute temperatures. This is the amplification question. How much higher will they be? And what are the threshold effects for specific impacts on agriculture, hydrology, and public health? This is precisely what the research community is urgently trying to determine, working under conditions of significant uncertainty and using models that are being pushed beyond their validated ranges. It is not a comfortable position for science, but it is where the data has led. In a very real way, the dual coast heat domes seen in early May are a small preview of the question posed by the 1877 analogue. They force us to ask, what does an event of that magnitude actually look like when it arrives on our modern, warmer baseline? Anytime an extreme weather event of this scale occurs, particularly one with such a clear and direct impact on large populations, theories about alternative causes tend to emerge. One idea that has gained considerable traction in social media discussions is the claim that the dual heat dome is the result of geoengineering some form of deliberate atmospheric intervention by a powerful government or institution. This claim deserves a direct and calm response, rather than a simple dismissal. In its most common form, the theory posits that activities like cloud seeding or so-called chemtrail dispersal are responsible for either creating or amplifying the current heat event. To evaluate this, we must consider the relevant physics. A heat dome on the scale recently observed simultaneously covering the entire Southwest and the Florida Peninsula, represents an energy budget of truly astronomical proportions. The thermal energy required to maintain high-pressure systems of this size and intensity for multiple days is on the order of petajoules to exajoules, quadrillions to quintillions of joules. To put that in perspective, the total energy production of all human civilization on Earth, including all fossil fuels, nuclear power, and renewables, amounts to approximately 600 exajoules per year. The energy budget of a continental-scale atmospheric pattern is simply not something any current or foreseeable human technology could produce, sustain, or control. Cloud seeding is a real and established practice. It can, under very specific conditions, influence local precipitation by introducing condensation nuclei into clouds that are already near saturation. However, its effects are strictly local, measured in tens of kilometers at most, and it is entirely dependent on pre-existing atmospheric conditions that the seeding itself cannot create. It cannot generate a heat dome. It cannot sustain a high-pressure system over a continent. It cannot produce a large-scale Rossby wave configuration. The energy scales involved are mismatched by many orders of magnitude. The immediate drivers of this heat event are well understood within the realm of atmospheric dynamics. A confluence of powerful forces, the omega block, a high-amplitude Rossby wave, deep subsurface ocean heat, and the ENSO transition are all at play. These are vast planetary-scale systems, operating on energy budgets far beyond any current human ability to influence in real time. This, however, is not to say that human activity is uninvolved. On the contrary, our actions have significantly contributed to the background warming that makes such events more intense. The mechanism is the slow, cumulative effect of greenhouse gas emissions altering the planet's energy balance over many decades, rather than some form of direct, active weather manipulation. Understanding this distinction is absolutely crucial, as it shapes both our diagnosis of the problem and the path toward a solution. Beyond these atmospheric dynamics, other explanations have been proposed for the recent warming. One prominent idea points toward the Sunday. The argument suggests that because we are in an active phase of the solar cycle, the increased energy from our star could be the primary cause of the temperatures we are witnessing. This is a perfectly reasonable hypothesis to investigate. Indeed, the study of solar forcing is a well-established field within climate science. It is only right that we turn to the observational data and see what story it tells. It is true that we are currently in solar cycle 25, a period that has proven to be notably energetic, even more so than many initial forecasts predicted. The cycle is reaching its solar maximum around this time, and objective measurements confirm this heightened activity. Sunspot counts and solar irradiance have been higher when compared to recent cycles, and events like solar flares and coronal mass ejections have become more common. By any standard, our sun is in a particularly dynamic phase. But does this activity on the sun translate directly to the heat we feel on Earth? When we examine the link between solar activity and surface temperatures on our planet, the argument begins to weaken. Firstly, the actual increase in total solar irradiance from a solar minimum to a maximum is remarkably small, only about 0.1%. This slight uptick in energy reaching our atmosphere is simply not powerful enough to account for the significant temperature anomalies being recorded. Furthermore, climate models are sophisticated enough to isolate the influence of solar variability from other factors. They show that while this cycle is active, it remains well within the historical range of variability seen in previous cycles. It is energetic, but not unprecedented. The second, and most critical piece of evidence, lies in the specific pattern of warming. If the sun were the main cause, we would expect to see the warming distributed more evenly throughout the atmosphere, with the upper layers warming at a rate similar to, or even faster than, the lower layers. However, our observations show the exact opposite. We are recording a cooling in the upper atmosphere, while the warming is concentrated down here, in the lower troposphere. This specific pattern is the unmistakable fingerprint of warming caused by greenhouse gases, which trap heat closer to the surface. The evidence we see in the sky is simply inconsistent with solar activity being the primary driver. In essence, the current heat event is happening during a period of high solar activity, but it is not happening because times of it. The relationship is one of coincidence, not causation. The true mechanisms are the complex, interconnected processes we have been exploring, the large-scale dynamics of our climate system, the transition in the ENSO cycle, the pronounced wave patterns in the atmosphere, and crucially, the elevated temperature baseline from which all these events now launch. The solar cycle is a real and important phenomenon to monitor, but it does not explain the extreme conditions unfolding before our eyes. Another perspective often raised is the argument from history, the idea that this is all just part of a natural cycle. This claim posits that events like these have occurred before, pointing to the 1930s and the comparable heat extremes of the Dust Bowl era in the United States. The conclusion is that today's heat domes are merely the latest manifestation of a natural variability that has always been with us. This framing holds both a powerful truth and a deeply misleading conclusion. The truth is that the 1930s did experience extraordinary heat. The heat waves of the Dust Bowl, especially in 1934 and 1936, were so severe that some temperature records set back then still stand today. Those events were catastrophic, fueling mass migration and agricultural collapse. It is undeniable that natural climate variability is a potent force, capable of producing extremes that can match anything in our modern records. The misleading part of the argument is the conclusion that today's event is therefore comparable, requiring no further explanation. But a simple comparison is problematic, as several critical differences separate our time from the 1930s. Firstly, the entire planet's baseline temperature is different. The global mean is approximately 1 degree Celsius warmer today. Our oceans are also substantially warmer. This is a key distinction, because the oceanic conditions that fueled the Dust Bowl heat were partly driven by times cold, times Pacific sea surface temperatures, which amplified the drought. Today, we are seeing warm times Pacific waters, which are currently in the process of becoming even warmer. Secondly, we now have records for subsurface ocean heat content, something unavailable in the 1930s. This data reveals unprecedented levels of heat stored deep in the ocean, with no parallel in the instrumental record from the 19th or early 20th centuries. A third crucial difference lies in the atmospheric patterns themselves. The Dust Bowl heat was largely a continental phenomenon, driven by feedback from the drought-stricken soil. This is fundamentally different from the vast, large-scale Rossby wave amplification we are observing now, which is creating simultaneous heat domes on opposite coasts. While natural variability is real and historical precedent is valuable, the context has profoundly changed. The underlying conditions of today's event, the immense ocean heat, the specific atmospheric configuration, the ENSO transition, and the timing, are not simply a replay of past cycles. They are unfolding on a warmer baseline, within a different oceanic environment, and are generating spatial patterns that are structurally distinct from their historical analogues. The climate system does indeed have cycles, but a cycle does not always repeat within the same boundaries. When the background conditions from which a cycle emerges are altered, the behavior of the cycle itself changes. The 1930s were undeniably extreme. What is happening now is different in ways that are critical for understanding the risks we face in the future. Let us now pull back from the details and view the entire mosaic that has come into focus. By assembling these individual pieces of evidence, we can begin to see the full picture of our planet's changing state. When we assemble the disparate events of a single week, side by side, the full meaning of this period becomes far clearer than any one piece of data could ever suggest. It is this complete picture, not just the alarming individual numbers, that reveals a pattern of profound significance. The data points alone are startling, but the tapestry they weave is something else entirely. During the first week of May 2026, two powerful heat domes materialize, with separate ridge systems peaking over opposite coastlines within the same 4-8-hour window. The western ridge subjects Phoenix to temperatures more characteristic of the sweltering peak of mid-July. Meanwhile, the eastern ridge, anchored over the Caribbean, funnels intense heat northward into the Florida peninsula. This onslaught challenges temperature records at stations that have maintained continuous, unbroken data collection for 155 years. South Florida finds itself under the highest alert from the National Weather Service and extreme heat risk, with overnight temperatures refusing to fall below 80 degrees. The implications of this are stark. At 3 in the morning, the air isn't cooling, the city isn't cooling, and the human body has no chance to recover. At the same time, 450,000 people in California are placed under extreme heat watches. 8 red flag warnings are active across the northern plains, and a corridor of severe weather cuts through Oklahoma. This is one atmospheric pattern, triggering 4 distinct hazards across 2 coasts. An event of this scale would, by itself, constitute a significant weather week. But the true anomaly here is not the intensity of the heat, but its timing. The calendar is where the story shifts. All of this is unfolding before the season has truly turned. Early May is a transitional time, the shoulder season between the cool of spring and the heat of summer. The atmospheric infrastructure needed to generate genuine July-level heat. A conditioned boundary layer, depleted soil moisture, and a fully established seasonal ridge is simply not supposed to be in place yet. The heat is arriving ahead of schedule, placing immense stress on a system that has not been seasonally prepared. This is precisely what forecasters mean when they describe an event as acting out of sequence. The established boundaries that provide meteorology with its conceptual framework, the very understanding of what is normal for May versus August, are being violated. They are not being nudged or slightly exceeded. They are being broken. The climatological norms are being surpassed not by a small margin, but substantially, in a manner that resembles peak summer, not early spring. This temporal displacement is the central, unsettling feature of the entire event. Now, let us widen our perspective, because the atmosphere does not exist in a void. It rests upon the ocean, which is currently behaving in a way never before recorded. In the Pacific, the amount of subsurface heat, the thermal energy stored in the upper 300 meters of water, has reached a level for April that is without precedent in the entire satellite monitoring record. We must pause to consider what this means. The satellite era represents roughly 40 to 50 years of continuous, modern oceanographic observation. In that entire history, the Pacific has never held this much warmth beneath its surface at this time of year. This includes the periods leading up to the major El Niño events of 1997 to 1998 and 2015 to 2016, which were long considered the benchmarks for powerful climate cycles. The word unprecedented is often overused, but in this specific context, it is the only accurate term. This extraordinary reservoir of subsurface heat is now dramatically influencing forecast models. The Niño 3.4 region, a critical section of the equatorial Pacific that effectively governs global weather patterns, is warming at a startling rate. The median projection from a consensus of models now points toward a peak anomaly exceeding 2.9 degrees Celsius above the long-term average. For comparison, the 2 most powerful El Niño events in the modern record peaked at approximately 2.4 and 2.6 degrees respectively. In a system where impacts scale non-linearly, an increase to 2.9 degrees represents a substantially greater force, capable of profoundly altering global circulation, precipitation, drought, and storm tracks. Some models in the ensemble are not even stopping there, with a few showing peak anomalies above 3 degrees Celsius. The upper range of this probability distribution extends into territory for which we have no observational benchmark in the modern era, no reference event, no historical analogue in our instrumental record. To find any parallel for an event of this projected magnitude, researchers are forced to look back to the El Niño of 1876 to 1878. The reason this name keeps resurfacing is because of what it did to the world. The resulting famine in South Asia led to the deaths of tens of millions of people. It pushed China into an agricultural crisis and caused massive disruptions in East Africa, Brazil, and Australia through a complete reorganization of global rainfall and temperature. It was one of the most consequential weather events in recorded human history. Today, scientists are cautiously using it, with all appropriate qualifications, as the only rough analogue they have for what the current models are projecting. It is a sobering thought that our most advanced tools are leading us to comparisons with a catastrophe from the 19th century. Perhaps one operational detail best illustrates how far outside normal territory these projections are. The vertical axis on the standard ENSO forecast chart, the graph that forecasting centers have used for years to display model projections, had to be extended. The numbers being produced by the models simply did not fit on the existing scale. The software itself had to be reprogrammed to display the output. When your very tools of visualization must be redesigned to accommodate the data, it is a clear sign that you have left familiar territory and entered genuinely uncharted space. This alarming week in May did not materialize out of nowhere. Its prelude occurred just 6 weeks prior. In March of 2026, a heat dome swept across the United States, shattering records with a comprehensiveness that stunned professional meteorologists. During that single event, more than 7,000 daily temperature records were broken, and over 2,000 monthly records fell. This earlier event served as a clear and unsettling warning of the atmospheric conditions that were already taking shape for the season ahead. A national temperature record for March reached 112 degrees Fahrenheit, a figure so extreme that forecasters at the time described it as belonging to an entirely different month. This event was categorized as one of the most severe heat episodes in the entire century of modern weather observation. It was the sort of occurrence one might historically anticipate seeing only once in several decades, perhaps once in a generation. That was just 6 weeks ago. Now, we have witnessed 2 such anomalous events, separated by only 6 weeks within the same season. Both were propelled by high-amplitude ridge behavior, and both manifested far outside their typical seasonal timeframe. Crucially, both coincided with a Pacific Ocean that is intensifying toward a state that our predictive models have never before been asked to forecast. In a climate system functioning within its historical range of natural variability, the odds of 2 events of this scale happening so close together are exceedingly low. These are phenomena with return periods once measured in decades. Seeing 2 in 6 weeks is not a coincidence that can be easily dismissed. It is a signal, and signals are the very language the atmosphere uses to tell us that something fundamental within the underlying system has already changed. When all the pieces are assembled, the heat domes on 2 separate coasts, the violation of seasonal timing, the unprecedented heat building beneath the Pacific, the record-shattering March event, the forecast charts that had to be physically redrawn, and the synchronized updates on El Niño probabilities from NOAA, the WMO, and every major science desk in the same week, a coherent and deeply unsettling picture begins to emerge. This is not a picture born of alarmism or speculation. It is the image that the data itself is constructing, piece by piece, in real time, directly in front of the very people whose job it is to watch. What this tells us is that the climate system is already expressing what appears to be peak phase behavior even before the true peak has arrived. The atmosphere is already responding to oceanic conditions that have not yet fully registered in our surface temperature records. The vast reservoir of warm water accumulating beneath the Pacific surface has not yet reached the top. It is still loading, still stacking its energy, and yet the atmosphere is already reacting with force, creating dual coast ridge amplification, compound hazard patterns, and extremes that defy the calendar, all before the oceanic heat has fully expressed itself at the surface. This is the very mismatch that has left forecasters quiet, not because they are uncertain that something significant is happening, but because they are uncertain how to communicate a significant event that is unfolding faster than our standard monitoring frameworks suggest it should. The formal thresholds for an El Niño Southern Oscillation event have not yet been crossed. The official declaration of an El Niño has not been made. Despite this, the atmosphere is already generating conditions consistent with a system that is much further along in its transition than the official indicators would have us believe. This gap between the threshold indicators and the actual behavior of the atmosphere is not a small one. It is visible, it is measurable, and it is sitting right there on the map. It takes the form of 0-degree afternoons in Phoenix in early May, and overnight lows that fail to drop below 80 degrees in coastal South Florida. This is precisely what elevates the current situation beyond a remarkable week of weather. It becomes a diagnostic tool. The atmosphere itself is functioning in real time as a direct readout of the underlying energy state of the entire climate system. And what that readout is telling us is that the system has already shifted beyond the calibrations we have long used to interpret it. Every heat record that falls in Jacksonville is another data point. Every overnight low that remains above 80 degrees in Miami is another data point. Every afternoon in Phoenix that nears 110 degrees before summer has even officially started is another data point. Viewed in isolation, each of these events can be contextualized, qualified, and placed within a familiar framework of natural variability and year-to-year noise. But when taken together, in this week, in this season, and against this oceanic backdrop, they converge on a single conclusion that is difficult to explain away. The system is already much further along than our official indicators suggest. The precursor is already triggering the main event. And this brings us to the question that is quietly preoccupying the people who are closest to this data. It is the question they are sitting with as they watch the model outputs, as they choose their words with immense care, as they update their probability estimates and publish their outlooks, all while trying to communicate something that has no clean historical precedent, using a language designed for situations that do. The question is this. If this is what the pre-peak looks like, 2 coasts in early May, compound hazards stacked across an entire continent, 155, year records falling in Florida, temperatures in Phoenix that belong to midsummer arriving before summer has even begun, and a forecast chart that had to be redesigned just to fit the numbers, then what will the actual peak look like? This is not a rhetorical question. It is the operational question, the one that emergency managers, utility grid planners, water resource agencies, and public health systems must be asking right now, in May, about conditions that models are projecting for October through February. The peak is still months away. The subsurface heat is still loading. The oceanic Kelvin waves are still stacking. The chart has already been redrawn once. And somewhere between the carefully qualified language of institutional probability assessments and a forecast that has no modern precedent in our observational record, that question is still waiting for its answer. The atmosphere, for its part, already started answering it this week. The only remaining question is whether we are paying close enough attention to hear what it is saying. What happens at the peak? Let us project forward carefully and honestly, with the appropriate amount of uncertainty attached to every claim, because the most truthful answer to the question of what comes next is that nobody fully knows. It is important to be upfront about this, because in a story of this significance, the temptation to reach for conclusions beyond what the data can truly support is very real. We will not do that here. But it is also critical to be clear about another point. Uncertainty is not the same as ignorance. In this context, the uncertainty itself is a significant piece of information. The very fact that the confidence intervals surrounding the coming peak are as wide as they are tells you something vital about the magnitude of what the models are projecting. You do not get wide confidence intervals when forecasting small, familiar events. You get them when you are forecasting in territory the system has never mapped before. Before we venture into the territory of what remains unknown, we can begin with what current climate models project with a degree of confidence. The models indicate that peak El Niño conditions are likely to arrive in the latter part of 2026, specifically within the October to December timeframe. This projection aligns with the established seasonal rhythm of ENSO events, which typically develop through the middle of the year, reach their zenith in the final quarter, and then gradually weaken through the following spring. This general shape and timing represent one of the more reliable aspects of the forecast, having been observed across dozens of prior events. The question of times, when times it will peak, seems more certain than times how strong times it will be. This window of October to December is roughly 6 to 8 months from our current vantage point in early May. In that intervening period, a series of profound changes will unfold. The record-breaking subsurface ocean heat, already at unprecedented levels for any April in the satellite era, will progressively mix upwards toward the surface. Over these same months, the sea surface temperature anomaly in the critical Niño 3.4 region will grow from its current value, which is already trending warm. And all the while, the atmosphere will be responding to this oceanic warming, building and intensifying new circulation patterns that will ripple across the entire planet. 6 to 8 months may sound like a generous amount of time, but for the systems that must prepare, it is not. Critical infrastructure, agricultural planning, and water management all operate on timelines that demand action now for consequences that will manifest in the autumn. It is within this gap between scientific projection and practical implementation that a significant portion of the risk resides. When we turn our attention to the potential impacts, we encounter a fundamental limitation in the science. This is not due to any weakness in the scientific method, but rather because the projected event may be genuinely beyond the range for which our scientific tools have been validated. Every part of the globe has a known statistical relationship between the strength of an El Niño and its local climate effects. These long-distance relationships, known as teleconnections, describe the pathways through which warming in the tropical Pacific travels through the atmosphere to influence weather thousands of miles away. The patterns are well documented. Southern California tends to get wetter, while the Pacific Northwest and the northern United States become warmer and drier. The Gulf Coast typically sees fewer hurricanes, but more winter precipitation. Drought can grip the tropical Pacific islands, while rainfall is reduced over southern Africa and Southeast Asia. Conversely, East Africa often receives enhanced rainfall, and parts of South America experience flooding. These patterns are not theoretical. They are real, reproducible phenomena found in decades of observational data, forming the basis for the seasonal outlooks that guide governments and agricultural systems. Herein lies the central problem. Those established teleconnection patterns were all derived from the statistical analysis of past El Niño events, and every single one of those events in the modern observational era reached a peak magnitude below what current models are projecting for late 2026. The most powerful event observed in the satellite record peaked with an anomaly of approximately 2.6 degrees Celsius in the Niño 3.4 region. In stark contrast, the current multi-model ensemble median is forecasting a peak above 2.9 degrees, with some individual models showing values at or even exceeding 3.5 degrees. When you ask a statistical relationship to perform based on an input value it has never encountered, you are no longer interpolating within a validated range. You are extrapolating. This process carries a fundamentally different kind of uncertainty, not just more of the same, but a qualitatively different challenge. We are, in essence, asking a historical map to guide us through a landscape it has never before charted. In practical terms, this means a 2.9 degree El Niño is not simply a more powerful version of a 2.4 degree event. It is not like turning up the volume on a familiar song. At a sufficient magnitude, ENSO events may not just intensify the familiar teleconnection patterns. They have the potential to reorganize atmospheric circulation in ways that could produce qualitatively different outcomes, new pathways, different regions affected, and altered seasonal timing. Places that have historically become wetter might not experience that moisture in the same way. Regions that typically become dry might grow even drier than historical relationships would predict, or they could be affected by an entirely different mechanism. The critical thresholds where the system transitions from amplifying a familiar pattern to creating a new one are precisely what the research community does not currently know with confidence. This is because there is no precedent in the modern observational record to calibrate the models against, leaving us in a deeply uncomfortable position when trying to turn model output into actionable guidance. For the United States specifically, the standard El Niño playbook would project a significantly wetter than normal winter across California and the Southwest, and given the projected magnitude, potentially a very wet one. The Gulf Coast states would also likely see enhanced winter precipitation. Meanwhile, the Pacific Northwest and the Upper Midwest would be expected to trend warmer and drier. These are the historical patterns, and they form the initial expectation even for an event of record-breaking magnitude. However, the confidence surrounding these patterns, the reliability of the historical teleconnection at this intensity and on this climate baseline, is considerably lower than it would be for an event within the historical range. This lower confidence does not mean the pattern will disappear. It means the uncertainty around exactly where, when, and how intensely it manifests is far wider than the historical data would suggest. The outlook for the Atlantic hurricane season is genuinely complicated. El Niño is known to typically suppress Atlantic hurricane activity by strengthening upper-level wind shear over the basin, which disrupts the organization of storms. By that logic, a very powerful El Niño should produce a relatively quiet Atlantic hurricane season in 2026 to 2027. But a major complication exists. The sea surface temperatures in the Atlantic are also significantly elevated above their own historical averages. These exceptionally warm Atlantic waters act as a potent fuel source for hurricane intensification, a factor that operates independently of the El Niño shear mechanism. This creates a potential paradox. We could find ourselves in a situation where the total number of storms is suppressed by the wind shear, but any storms that do manage to form can undergo rapid intensification over the anomalously warm water, offsetting the numerical suppression. The outcome could be a season with fewer storms, but the ones that do develop could be far more intense. A scenario where traditional metrics for a quiet season may no longer tell the whole story. Whether this delicate balance ultimately reduces or amplifies risk is a question that depends entirely on the specific paths these storms will follow. Predicting those tracks remains one of the most formidable challenges in operational meteorology, a fact that carries profound human consequences. The implications for agriculture are particularly direct, representing a space where the cost of a flawed forecast is measured in tangible human terms. For California's vast Central Valley, for instance, a winter with heavy El Niño rains has historically been a blessing, replenishing reservoirs and recharging precious groundwater. The subsequent dry season can then begin from a position of relative strength, but this benefit can quickly become a liability if the precipitation arrives too intensely for the infrastructure to manage. This is an increasingly critical constraint, as rainfall now trends toward shorter, more violent bursts rather than a steady seasonal accumulation. Even if the total volume of water is the same, its arrival in a sudden deluge is a completely different scenario than a gentle, season-long soaking. California's reservoir system was engineered for a precipitation pattern that is already being altered by background warming. When you superimpose a record-breaking El Niño onto this already stressed system, the line between relief and disaster becomes a matter of timing, not just totals. The situation is quite different for the grain belt in the central United States. An El Niño winter typically brings enhanced warmth and dryness to the upper Midwest, directly impacting soil moisture ahead of the critical spring planting season. If this pattern proves more intense than historical examples suggest, or if the atmospheric connections push the dryness further than anticipated, the result could be significant soil moisture deficits across one of the most productive agricultural regions on Earth. The ripple effects of such a deficit would be felt throughout commodity markets and the global food systems that rely on those harvests. In the tropics, however, the narrative becomes even more severe. For the small island nations of the tropical Pacific, an El Niño-induced drought is not a distant concern. It is an immediate water security crisis. For the nations across Southeast and South Asia that depend on monsoon rains for their agriculture and water supplies, a reduction in that rainfall from a record El Niño is not a mere weather inconvenience. It is a full-blown food production crisis. We have seen this before. The El Niño of 1876 to 1878 led to the deaths of tens of millions, primarily by disrupting the monsoon systems that sustained the world's most populous areas. Today, those populations are even larger, and the agricultural systems are more intricate and globally interconnected. The exact mechanisms of impact would differ, but the fundamental exposure of billions of people to monsoon disruption has not diminished since 1877. It has only grown. It is essential to state this clearly, without unnecessary softening. None of this means that a strong El Niño is an exclusively negative phenomenon. It is not. These events often bring genuine, desperately needed relief to regions suffering from prolonged drought. They recharge water systems that have been dangerously depleted. They can also suppress Atlantic hurricane seasons, which has historically led to fewer storm-related fatalities and less damage to infrastructure. The true picture of its impact is always a complex mosaic, varying by region and depending on the precise timing and character of the event. A powerful El Niño creates a world of contrasting outcomes, and both the regions that benefit and those that suffer are equally real. What makes the current situation so profoundly different, what separates this moment from discussions of any past El Niño, is that the potential magnitude of this event lies beyond the scope of our historical experience. The established calculations of benefits and costs simply may not apply. We have a rough understanding of what a 2-4 degrees Celsius El Niño can produce because we have observed it. We have no modern observational data for what a 3.2 or 3.5 degree event might unleash, because we have never witnessed one. And we are not approaching this uncharted territory from a neutral starting point. We are doing so from a background climate that is already warmer than the baseline upon which any previous El Niño peak was ever superimposed. The foundation itself is hotter, and the signal on top of it is potentially larger than anything seen before. What these two factors will produce in combination in specific regions, at specific times, and within infrastructure systems designed for a climate that no longer exists, is the new terrain we are now entering. The forecasters who watch the model outputs are acutely aware of this. You can sense it in the deliberate, measured language they choose. You can feel it in the gap that exists between the raw data the models are showing and the carefully worded public communications. They are not hiding something from the public. Rather, they are doing precisely what good scientists do when their data pushes them to the very edge of their validated knowledge. They are being careful. They are being honest about the profound uncertainty. They are attempting to communicate something genuinely unprecedented without making exaggerated claims that could undermine their credibility when precision is most critical. But in the space between that cautious language and the forecast charts that had to be redrawn to even fit the model outputs, a story is unfolding. In that space, the atmosphere is already acting. It already did something remarkable in March. It is doing so again right now, on both coasts simultaneously. In early May, a time that should be a quiet prelude before the event's peak. We are moving toward a peak that no modern climate system has ever experienced, set against a background temperature that has never been this warm. This is all being driven by subsurface ocean heat that has never been this high in April, and it is already producing atmospheric signals that look more like mid-cycle behavior than pre-season calm. That is the terrain that lies ahead. The models can see it coming. The crucial question is whether everyone else is looking in the same direction. Here, I want to return to where we began and spend some real time, not on the temperatures, the records, or the model projections, not on the atmospheric mechanics or the heat content of the Pacific. All of that is critically important, and we have given it considerable attention. But the single most compelling aspect of this entire situation, the element I keep returning to when I look at all the data assembled before us, is not any of those numbers. It is the behavior of the very people whose job it is to tell us what those numbers mean. The forecasters are quiet, and I want to be very precise about what I mean by that word, because their quietness is not the same as silence. On the surface, the systems of global observation and warning appear to be functioning perfectly. Extreme heat risk advisories have been dispatched to South Florida, and similar watches are in place for 450,000 residents of California. Across the northern plains, red flag warnings remain active and are being consistently updated. Official bodies like NOAA's Climate Prediction Center have formally communicated their elevated estimates for El Niño's probability, while the World Meteorological Organization has issued its own alert regarding its rapid development. The briefings are being held, the outlooks are being published, and the lines of communication are open. And yet, if one reads these communications with an eye for what is not being said, a subtle but significant shift in language becomes apparent. This is not the confident, specific tone that characterizes forecasting within familiar parameters. The qualifications are more frequent. The probability ranges are wider, and phrases that would commit to a particular outcome are conspicuously absent. The language is undeniably accurate and responsible, but it is measured in a way that suggests something other than comfort. This deliberate restraint raises a critical question. What does it mean when experts, seeing something new, choose their words with such profound care? In the familiar world of routine forecasting, communication rests on a foundation of historical precedent. Experts can reference past events, noting that a current weather pattern resembles the 1997 Ridge event, for example, and therefore similar conditions can be expected. The models they use have been tested against these analogous situations, giving them known performance characteristics and empirically derived uncertainty bounds. This is not a theoretical exercise. It is a process calibrated by real-world outcomes, where forecasts were made, events were observed, and confidence levels were adjusted accordingly. In such a scenario, forecasters have a clear map of what they know, what they do not, and the territory in between. This established process is the bedrock of modern forecasting, allowing for the confident and specific communication we have come to expect. Now, however, forecasters find themselves at the very edge of this validated range, navigating a landscape where the old maps are no longer reliable. The figures being generated by their models are unlike anything seen in the operational record. The historical analogues they would normally turn to are either completely absent or so distant in time, like an event from 1877, that they are functionally useless. An 1877 event occurred long before continuous instrumental monitoring, before satellites, and before the modern data infrastructure that gives today's models their predictive power. As a result, the uncertainty bounds are no longer calibrated against past performance. They are theoretical, derived from model structure, rather than a track record of forecasting something comparable. This forces scientists into uncharted territory, where the usual rules of engagement no longer apply. This new reality fundamentally changes how information can be conveyed. The confidence of routine forecasting is simply not available when you are navigating territory for the first time. This is why certain words, like unprecedented, are used with such caution. The term is not avoided because the data fails to support it. In fact, the data supports it clearly and unambiguously. It is used sparingly because the moment it is uttered, it triggers a cascade of follow-up questions about impact. What does an unprecedented event mean for agriculture, for the power grid, for water management, or for the monsoon rains that entire regions depend upon? An honest forecaster knows that their confidence in answering these impact questions is far lower than their confidence in the initial observation, so they hedge and qualify, choosing language that conveys the seriousness of the situation, without implying a certainty of outcome that their models, now stretched beyond their validated range, cannot provide. This careful choice of words is a practice known as professional epistemic humility, and it is a difficult and admirable act. At the very moment when the public most desires certainty, the scientific community is tasked with accurately representing the limits of its own knowledge. When everyone is searching for a clear answer about what is to come, the most honest response is that a completely clear answer is not yet available. To state this plainly and repeatedly, in the face of immense institutional and public pressure to project confidence, is a form of integrity that deserves recognition and understanding, not frustration. In an age that demands simple answers, the most courageous response can be to honestly state that the full picture is not yet clear. But there is another layer to this story, a shadowy counterpart to this humility that also deserves to be named. The scientific and forecasting community has operated for decades within a social environment where the consequences of miscommunication are severe. If they forecast a major event that fails to materialize with the predicted intensity, they face accusations of alarmism and crying wolf, eroding public trust. Conversely, if they understate an event that proves to be more severe than communicated, they are accused of lulling people into a state of complacency, failing in their basic duty to protect public safety. This repeated experience of being criticized from both directions has cultivated a distinct communication style, one that relies on hedging, careful qualification, and a strong institutional pull toward the most conservative interpretation of the data. This pull toward the conservative case is not irrational. It is a rational defense mechanism, born of real institutional experience and the high reputational stakes involved. It reveals how the very act of communicating science is shaped by the social and political currents it must navigate. When observational data begins to strain the limits of established conservative interpretations, a fundamental tension can arise. A gap can emerge between what instruments and models are revealing and what is being conveyed in public communications. In this space, information that could be vital for public decision-making may become suspended in a kind of institutional limbo. It is known to the forecasters and visible within the data yet it struggles to transition into public language with the weight it arguably deserves. In the spirit of transparency, it is helpful to examine a synthesis of the available data, not as a formal conclusion from any single institution, but as one reading of the current situation. This perspective suggests that the climate system has already entered a state of behavior that is more energetically advanced than what formal monitoring thresholds for the El Niño Southern Oscillation, or ENSO, would typically indicate. The question this raises is whether our existing frameworks are fully capturing the speed and intensity of the changes underway. Considered in isolation, the March heat event could be viewed as a remarkable outlier. The simultaneous heat event occurring on two coasts might be explained as an unusual but understandable atmospheric configuration. Taken alone, the record-breaking subsurface heat content in the Pacific is a concerning precursor, and the model projections, so extreme they required an extended graphical scale, are, by themselves, uncertain extrapolations. Yet, when these events converge in the same season, and in the very same week that the world's leading climate institutions are all revising their El Niño probabilities upward, a different picture emerges. This convergence points toward a system not merely transitioning toward a peak, but one already expressing that peak's influence in ways our frameworks for a pre-peak phase cannot fully accommodate. If this interpretation of the data is accurate, then the relative quiet from forecasters may not stem from uncertainty about whether something significant is occurring. The observations themselves seem to have resolved that question. The atmosphere provided an answer in March, and it appears to be doing so again in early May across multiple regions. Instead, the unresolved issue, the one generating the restraint and carefully chosen words, is how to communicate a significant event that lacks a clean historical precedent, especially when the models describing it are operating beyond their empirically validated ranges. This is the core of the communications dilemma. This places scientists in a profoundly challenging professional position. Imagine watching something unfold in real-time data that your training and experience tell you is deeply significant. You possess the technical expertise to understand the mechanisms at play and the general direction of events. At the same time, you are bound by a critical and appropriate scientific norm. You must not communicate beyond what your evidence can rigorously support. The paradox is that the evidence is pointing toward phenomena that are difficult to support with rigor, precisely because they have never happened before. The precedent that would ground your claim does not exist. You are witnessing the precedent being set. And so, the response becomes one of meticulous process. You watch the data, you issue updates, and you choose your words with extreme care. You release the alerts that current conditions warrant and publish the outlooks that the models support. The probability estimates are raised as the data justifies each step. And somewhere in the space between all of these necessary actions and the full weight of what you suspect you are witnessing, you must sit with a unique professional tension that has no easy or clean resolution. The dual heat domes of early May are a signal. The March event was a signal. The immense heat stored below the Pacific's surface is a signal. The model outputs that demanded a redesigned chart are a signal. Each of these, held individually, can be contextualized and qualified within frameworks that require no extraordinary claims. An explanation can be found for each one that fits within the known boundaries of atmospheric and oceanic variability. But signals are not meant to be held individually. They are meant to be read together, and when read in concert, in the same season, pointing in the same direction, and set against the backdrop of record Pacific heat, they form a picture that makes it difficult to conclude that the underlying system is behaving as usual. All the while, the forecast models continue to run, producing numbers never before seen in the operational history of ENSO forecasting. The atmosphere itself seems to be ahead of its own seasonal calendar, and the ocean is holding a level of heat for April that has no precedent in the satellite record. The real story, then, lives not in the temperatures or the specific Celsius values of a projected anomaly. It lives in the quiet, meaningful gap between these powerful data points and the public language used to communicate them, in the space where the people closest to the data are grappling with the distance between what they can see and what they can formally say. Ultimately, a forecast that has never been made before presents more than just a scientific challenge. It is a preparation challenge, an infrastructure challenge, and a profound policy challenge. How a society plans for a projection with no historical precedent, how it builds systems capable of responding, and how it communicates the risk to the public to foster preparedness, rather than panic or complacency. These are questions that extend far beyond meteorology. They are fundamental questions about how we navigate a future for which no map exists. The time to begin answering them is not in the months ahead. It is now. In May, the crucial decisions that will define our readiness for the approaching peak are being made. Those responsible are relying on forecast charts that had to be physically redrawn simply to accommodate the unprecedented output from their models. The atmosphere itself recently provided a stark signal, a single weather pattern affecting 2 coasts well ahead of the peak in early May. The issue is not whether this warning is being understood by those monitoring the data. The evidence suggests it is. The real question is whether the response is unfolding with the necessary speed and scale that the implications demand. Based on the deliberate quiet from the institutions tasked with informing us, it is difficult to assume the gap between the signal and the action is as narrow as one would hope. All the while, the models generate figures for which no precedent exists, and the time between now and the season's peak continues to shrink.